Oh yeah, right, trustworthy AI. That is the subject of my talk today. Practical collaborative engineering. So I'm going to unpack what that title means a little later on. But fundamentally, I think, have I got 30 minutes or 25? 20 minutes. I'm going to go through two things. One, I'm going to attempt to summarise the results of the consultation exercise we went through with TechWorks, share with you some of our findings and possible next steps. And then for the latter half, I'm going to dig into this tie bomb concept, this trusted AI bill of materials that we are proposing, one of the first initiatives we run under TechWorks. But just before I do that, so trust in AI, why is it relevant to me? What have I got to say about it? So in a former life, I was CTO of OMTP. David Rogers was the head of security. He was in this building. I'm not sure he's here now. So the OMTP was the standards organisation that looked after the trusted execution environment. Some people know what that is. Those of you that don't, you've probably got about 3 of them on your body at the moment. So there'll be one in the SIM card, one in the mobile phone, and one in your laptop. Whatever. It's fundamentally the hardware sort of trust foundation for pretty much all modern computing. As CTO of the organisation that standardised that, I have a little bit of experience on what it means to bring trustworthy technologies to the mass market. On the AI side, as John said, I did my PhD in AI a while ago. This is just one of the papers that I wrote in the early 1990s. I used to still write papers. When I was still at school, I was implementing neural networks in 6,000-8,000 assembly using fixed point maths. An unusual childhood. I've been doing AI a long time, principally in academia. But the reason I'm going into that is not to really show off what I know about the subject, but more in a Rumsfeld-esque way, explain what I know I don't know. And I think this is the important sort of like foundation of doing something important in this area. You know, AI is moving at such a rapid rate. There are so many sort of like snake oil salesmen sort of selling you solutions to X, Y, Z. It's important to have a good, strong foundation of what is known and what is unknown to move forward. And I'd say the two things that I don't know, I don't really know what trustworthy AI is, and I don't really know how to build it. But I think I know where to start. And one of the places to start, I think, is in, and this is why we're collaborating with the TechWorks community, is we need to start with a group of people who are very well versed in what it means to build technology. And I think that's one of the reasons I like working with the TechWorks community. They're not really strategists, they're not academics, they're not consultants, they're people that build things. And I think that's a great place to start. And the title that I picked, Practical Collaborative Engineering, was very deliberate because whatever we decide to do in this community, firstly, it's got to be practical. It's got to be something we can do and work on and talk about. It's got to be collaborative, so there must be net benefit for all of these organisations working together. If it's just a new optimised algorithm, you don't need to collaborate on that. You need to find the topics for which there is mutual benefit, and it should have an engineering focus in line with the sort of like the TechWorks mission statement. So basically, over the summer, there were a number of webinars and face-to-face workshops. I mean, those workshops were very well attended. I think we had about 60 of different organisations, some very deep, wide-ranging conversations, which I was given all of the white papers afterwards and tried to summarise it. So I did my best. I won't pretend it's perfect. But the challenge was, from those wide-ranging discussions, trying to work out, so what can we do? What's practical? So the link to that paper is available on the website. I've copied it up here. And basically, it's a triaging process, a load of questions, all very interesting, but probably not the right things for TechWorks to look at. And then a whole load of questions, which, do you know what? I think we might be able to take a punt at some of those. So the questions that essentially de-scoped for what is AI, well, I don't know. Actually not a question that interests me very much. I think it's just playing with semantics. Can the outputs of an AI system be explained? That's a really good question. It's a really hard question, but it's a research grade question. It's not something that you're going to make short-term sort of like engineering progress against. How do you ensure fairness and prevent bias? I sort of put that in the same bucket. as a sort of like an engineering-focused innovator, you know, if I can mathematically encode it, I can do it. But you know, I can give you some very interesting hard-won stories about just how difficult it is to frame bias in a practical way. So does UK industry have access to the necessary capability and skills? I mean, a very important problem that was raised. But I think this is being addressed elsewhere. I mean, Gopal mentioned the massive variety of CDTs that are being spun out, and there's all sorts of training. But it's not really like a TechWorks direct problem to look at. And does UK have the infrastructure to train large AI models? I mean, similarly, I'm aware a lot of central government UK money has been targeted at that. Therefore, it's not something sort of like directly on the TechWorks radar. So what about the ones in scope? So there's a whole host of questions here. I'll run through fairly quickly. But the common thread of all of these is we believe that the technology we're proposing, which is this new AI bill of materials, has something meaningful to add to these problems. So how do you know that an AI behaviour system will be changed? So this is a very, very foundational problem we're looking at, which is the versioning problem. Well, what is stable about the AI? How do I know the system we're using today is going to give me the same results tomorrow? There's a whole set of questions about best practice. I think William, who's talking after me, is going to address those topics sort of like a little bit better, and that's sort of a separate thread of what TechWorks will be looking at. How do we confidently test an AI system? I'm not sure I know how to test an AI system, but we've got some interesting proposals how we record the results of those tests and how we can share the results of those tests. Who is liable when there's damage done to the system? Well, that is a quite complicated, knotted problem. And sort of like a tide issue, sent to trade. I think this is going to be one of the biggest problems going forward. This is all of the large sort of like neural network-based AI systems are dependent on data. Who owns that data? Did they give their consent for that data to be trained? What is the legal relation that exists between the data owner and the model provider? Really, really complicated problems. If regulation goes one way or another, it could actually wipe out entire industries. So that is sort of a narrow part of the problem. So where did it come from? You know, what's the provenance of the system? Which again is tied to, well, trustworthiness is obviously dependent on the hardware you're running on. And it's obviously dependent on the software that you're running on. So some sort of ability to start tracking the dependencies of the system seems to be quite critical in terms of actually building a trustworthy system. There's a question of context, what it's being used for, and subjectivity, which I'm going to jump into shortly. So just a few slides in terms of framing the problem. So most of you probably know this anyway, on those with electronics sort of backgrounds. Almost all modern computing systems, hardware and software, can be expressed as an AND gate. It's quite a phenomenal thing when you actually understand it. One single gate, when you build them at enough complexity, actually models all computing as we know it. Likewise, for neural network, pretty much everything decompresses to the neuron model. You know, it's a set of weights that are aggregated, and there's an activation function. But these fantastic sort of like LLM systems are all pretty much built off that same tiny little compute component. And here's something, so the first bit might be stunningly obvious to you, which is each and every one of those massive neural networks is actually simulated on the NAND gates. So there's this abstract, soft, fuzzy processing node is modeled at volume on the tiny little transistors and NAND gates you get in the silicon. But also, interestingly, the inverse can also be provably true. Certainly for subsets of neural networks, with the current neural networks, that you're possibly to simulate the whole sort of like Turing machine. So you've got this interesting sort of inversion of these two computing paradigms that can sort of be computed to each other, albeit not necessarily optimized. So if you take one thing away from this entire talk, it's probably this slide, which is sort of just explaining the complexity of determining trustworthiness in a neural network system. So, classical networks, you've got two subsets here. You've got the inference machines, and you've got the training machines. So the inference machines are the things that you deploy, right? That's the sort of like the compute element that's doing the clever thing, whether it's a large language model or whether it's the thing looking at your CCTV camera. But in terms of the dependencies there, well, if I'm going to trust a system, the first layer is the physical hardware layer, the piece of silicon that the stuff's running on. Then on top of that, I've got to overlay the operating system and the base level of software. Then on top of that, there's the implementation of the inference algorithm. Then on top of that, there's probably a few small number of configuration parameters. And then on top of that, you've got your weights, which I'll touch on the size and the scope of this in a minute. So this is the full chain of trust that needs to exist at the point of deployment. But as you see, there's a red line there between the inference machine and the training machine, because the functionality of the inference machine is totally dependent upon the weights, and that's coming from n number of training machines. And each and every one of those training machines has got the same set of dependencies. So this is a simplified view, but this is the view of what real world, like, sort of AI deployments, currently look like. And it starts to give you a sense of the dependencies of trust that you need to track and monitor. So then let's overlay the issue of sort of like dimensionality. The trouble is the numbers being taught here, you tend to get number blindness and you sort of like lose track of just how massive it is. So as John said, the current state of the art silicon, 80 billion transistors. Right? And there can be many of those, both on the training side and the inference side. And the reality is, a single flip of a bit of any one of those can destroy the trustworthiness of the entire system if it's the wrong bit. You've got the training weights, so for ChatGPT-4 it's about 1.76 trillion parameters. You've got the basic sort of common or garden software, the operating system, so the Linux kernel is 27 million lines of code. But just to put this in context, just managing software trustworthiness and software bill of materials is really, really hard. And that's just 27 million lines of code. And then, what's that all resulting in? It's resulting in training data, again, using ChatGPT-4 as a reference, that's 13 trillion, you're using, the whole system has been trained on 13 trillion tokens. And obviously, your system is dependent on the data that you're training on. So what does this mean? If you want to trust the AI system, which bit you need to trust? Well, clearly, you've got to trust all of it, every single aspect. And as I said earlier, a change in a single bit or a single weight in one of those neural networks can actually destroy sort of like the trustworthiness of the system. So what seems obvious to us is layer one of establishing a trustworthy AI system is being able to describe it. If I can't describe it, what else can I do? And therein lies sort of like the major thrust, or the sort of like the first layer of innovation that we're trying to build into the type. So just a few words on trust. It's a slippery subject. I've got a talk that goes on for hours on this, but I'm just going to pick up two themes. First, what is trust? Trust is subjective, right? Or it's linguistically minded, it's not linguistically intransitive. What does that mean? I can't say this machine is trusted. It makes no sense to say this machine is trusted. Because what counts is who's trusting it. And I use my Cisco Huawei example as a great example, because do I trust a Cisco router? Does Vodafone trust a Cisco router? Does China Mobile trust a Cisco router? It's a completely inverted paradigm when you put Huawei in the picture as well. And this level of subjectivity of trust is almost enacted into law. So it's quite clear that trust is not a static attribute of the system. It's a subjective attribute. It changes over time. It's dynamic. What I trust today, I might not trust tomorrow. And it's also subjective. It's entirely independent of what I'm going to do, so what I'm going to use it for. It's highly parameterized. And the second part, I think I've already touched on already. Trust is transitive in the mathematical definition rather than the linguistic definition. But what I mean by that is obviously, if A trusts B and B trusts C and C trusts C, I need that entire chain to be true if I want the whole thing to be trusted. And I think I sort of explained that in the earlier slides in terms of the layering. So that's the concept. So what exactly are we going to do about it? So Taiwan Trusted AI Bill of Materials is a newly triggered project. I think it's currently being sort of seed funded by Innovate UK. As collaborators, it has sort of TechWorks, ourselves, Inquiring Minds, Copper Horses, British Standards Institute and BAE. But I think it's important to emphasise that is just the start, right? That is not the ambition. The ambition is to grow this into a much sort of like bigger collaborative initiative. And fundamentally, we're looking at two very concrete engineering-focused challenges. How do we delineate the AI systems we are measuring? So what is the labelling versioning problem? And then not necessarily how do we measure it, but how do we record the results of measurements of trustworthiness? And I'll dig a little bit more into what I mean, to be honest, in a minute. And in terms of what we're actually doing, so in terms of the objectives are to produce AI system descriptions, and to produce a system for creating sort of attestations of trust in the system. And in terms of how we're going to do that, well, it's a classic sort of standards dichotomy thing. The ambition is to produce a set of interoperable standards for making those descriptions, and that will be public, you know, sort of like open standards, sort of like promoted through the TechWorks community, but then also on a more proprietary basis, a set of software tools to actually enable that ecosystem. And we've got an idea of what it looks like. We've got an idea of what the building blocks are. And this work's been informed by work we've done previously within TechWorks on device security. It's also manifesting some of the work that's we've been doing with NIST. On device security, but it's just a much more mature manifestation for a much bigger problem. So the building blocks are something called, or the building blocks we are proposed to using verifiable credentials. So if you've not come across them before, they're essentially like digital certificates on steroids. They're defined by W3C. If you read the specs, there's a little bit of blockchain nonsense, read through it, ignore that. You can use the basic concepts of verifiable credentials. And essentially what they do is they embody the original vision of a web of trust. It's a way of describing the relationships between organizations with no central authority. And we believe to describe an AI system, you need these type of building blocks. So we've got a strong idea of what the underlying sort of primitives are. We've demonstrated it in narrow domains like IoT devices. And really the idea is we now just sort of like escalate it to a much bigger problem, which is the AI problem. And so just taking the earlier diagram and simplifying it even more, if we just had a set of cryptographic primitives for describing the compute host, the algorithm, and the training data, the weights that you're running on, you're already so much further on than you are now. I mean, you can go much deeper and you can describe many more relationships, but you know, my view is, if you don't have that, I don't care what test of bias you've got, what test of process you've got, unless I've got something stable I can put that label to, you don't have anything. So this is why we see it as the core sort of like foundational piece of tech. And I'm glad to say we're not the only ones. CISA has published something quite similar. It's all very early days, and you know, we intend on sort of like collaborating as fully as we can, but they spotted the same thing quite early on, which is software bill of materials, which I've mentioned yet already, but software bill of materials is good foundational technology. It is enacted in law in the US. And I'm always quite surprised the UK government doesn't seem to have a more coherent sort of like approach to it at the moment. But you know, from a pure security analysis perspective, it's sort of like, it's just common sense. Right? If I want to trust the software, I need to be able to trust the components from which the software was built. So that problem is part solved. The problem of solving sort of like the AI system problem just adds a little bit more complexity, because you want to add sort of like the hardware dependencies, what's called the CBOM, as well as the data dependencies as well. And remembering again is even when you describe the full system and the weights, at the end of the day, if someone's poisoned your training data, you're still screwed. So you need to be able to have a system for being able to sort of map that dependency to see where the problems are. So, very, very simply, it consists, or the proposal consists of 3 parts, which solves 3 core problems. The labeling and versioning problem, right? As per my diagram earlier on, every single element, I need to be able to label it and version it if I want to make any statement of trustworthiness against it. The second problem that it needs to solve is the dependency problem, because each of those individual components is dependent upon the other components, and in the case of a trained system, where you've got an invisible dependency on your training environment, you need to be able to map that out. So that's the sort of like the second sort of like challenge that we're addressing. And the third one, which is the most expansive in the long term, is the attestation problem. So whereas if we solve the first 2 problems, then we can describe a stable system. If we solve the final one, the attestation problem, we can then start describing it. So this could be as simple as, I run a test to show that my training data set has not been poisoned, to I run a test to show that the software on which I'm running doesn't have any disclosed vulnerabilities, through to, it's not a test, but when I built the system, I made a self-declaration statement that I follow best practice. Each and every one of those is a different dimensions of trustworthiness, but if we embody them in a very, very simple sort of like manifest that's cryptographically signed, then we've got a way of describing a more complex system. And I think those innovations are foundational, and I say more foundational, I'd say they're essential, because I think a lot of the other discussions about AI trustworthiness becomes a little bit opaque and flimsy without that foundation. But just examples of, once you've got that, the things that you can do. What are the primary use cases we see this? Well, firstly, any form of distribution, any form of AI store, whether it's Hugging Face or whatever, what you expect is, well, do you know what? I'd like my system to be described this way. I'd like to know what data sets it was trained on. I want to know, whether the software that I'm going to be running has been checked by someone that has any vulnerabilities. But, sort of, most even basic app stores have a very, very crude form of this. AI systems just need it to be a lot more sophisticated. The second problem, which I think is going to be very, very common, is AI systems inventory. So whether you're, running a ship or a car or a complex enterprise system, your security perimeter, your vulnerability surface is described as the union of all of the AI systems that you're running. So what do you need to do? Well, I need to be able to run through and sort of like understand every single AI system that I've got and be able to describe the dependencies on which it is built. And I don't know whether you've seen it, there's this, well, it's not actually a new initiative, Content Credentials Consortium was created some time ago. So this was an organisation that was created by the big sort of like Adobe's and the Microsofts or whatever as a method of signing sort of like data and outputs and stock images. They're obviously on this problem and have started to look at, well, how do I now add the attributes to describe the fact that it's being built within our system? It's the same concept, but just a lot more sophisticated and a lot more detailed. And then the final one is, the operational chaining. And this is sort of like really where the rubber hits the road. Whereas the first 2 use cases are static description problems, sort of like describing the sort of like the store or content distribution mechanism from which I'm downloading a system, or the second use case is the inventory. This is a lot more sophisticated. This is the concept that any AI system, when it produces the results, you can use the manifests and you can use the stamps to give you confidence this is where it came from. So this is a stretch goal. I think we're a long way off this, but hopefully clearly you can see when you put all the building blocks in place, you can start to see the engineering building blocks from which the solution can be built, but also practically how and why it's so useful. So that's really all that I had to say on substance. I think today is the first real official launch of this initiative. There will be a number of initiatives run under sort of like technical program. This one was by AI Bill of Materials. It's early days yet, and I think the first place to register interest is probably on the same sort of like website we went to this conference. Happy to take the sort of like questions now or by email later. And I believe there is a press release that if not hasn't gone out now, will be going out shortly, which basically is a very, very high-level introduction to the overall program and what's going to be happening next. Thank you very much.